It's a very simple instruction which you just write to your field, but it does a lot of stuff. So first of all, what it does is it forbids to cache, like if you put a field is volatile, then it forbids to cache that field in a register. And this is, by the way, what volatile means in C++, and a lot of guys who come from C++ to Java, they think this is what volatile does in Java as well. But this is not the only thing it does in Java. So the reason why it forbids to cache in registers is because if you cache a value in register and you write in one thread, then it will never propagate to any other threads. Other cores will never see it. The next thing that it does is that it issues memory fences. So it issues memory barriers. So it issues, and there are two causes for that. One is to make sure that the values that you write into cache are visible in the other caches, as I said. And the other is to make sure that there are no CPU reorders around them. So it puts these nice memory barriers. In addition, it guarantees atomicity. So it guarantees that, for example, if you write a long value, then on many platforms it's actually going to be two instructions, like writing the lower 32 bits and the higher 32 bits. And by all means, you don't want the other thread to see only the lower 32 bits return. So it guarantees that the other thread will not see the value before it's actually fully written. And it turns out it does another thing, because besides the hardware, which reorders reads and writes, the GAT is nice enough not only to reorder the reads and writes, but also to optimize some of them away altogether. So if you're writing to a field and you can guarantee that this field is not visible by any other threads, then it will actually, and you never read the field, then it can easily optimize away the write, because nobody ever will see it, and you can actually create very easily code that shows that it happens. Like you're writing to a static variable and nothing else sees it, because if the variable isn't, if the field isn't volatile, then there's no guarantee that any other thread sees it, so it can just create a copy per thread and be happy with that, or just optimize the writes altogether. So it's pretty damn, it's a pretty damn complicated thing. But it turned out it's not just that this is actually the easy part. So interestingly enough, once you understand what volatile does, you have to understand also that this isn't the same thing that synchronized does. So most people tend to think about synchronized as a critical section, or just as a lock. We take a lock at the beginning, we release it at the end. So if other thread tries to take the lock at the same time, of the synchronized block, if other thread tries to take a lock at the same time, then they wait until the lock is released, right? So this is a part of what synchronized does, but we have exactly the same problem inside synchronized as we have with volatile. If you have any writes to fields inside synchronized, so all of the writes have to have a read fence, a read memory barrier issued before the synchronized block, and a write memory barrier issued after the synchronized block. Well, depending on the architecture, again, because the GAT will issue as granular memory barriers as it can. So if it can, it will issue, per value. If it can't, it will issue, a generic memory fence or something. And here where it gets kind of interesting. So we have to worry about this multiple chips, about this multiple caches on kind of a lot of level of Java. And remember when I was talking about caches, I was telling that there's we have to broadcast, we have to snoop, we have to what else do we have? So this is a typical, this all a typical distributed memory, distributed system terms. And if you think, then already on this very low level of 2 cores and the shared memory, we have a typical distributed problem where we have 2 systems with local memory, we have a shared remote memory, we have a bus connecting them, we have broadcasts, we have snooping. So these are all a typical distributed system. And here's the thing, and here's why I was talking so much about it. And one of the things I want to one of the main things I want to talk about is that nowadays, even if we're working on on your own development machine, on your own laptop, you already have dealing with a distributed system. You can never again think that you have a single system and you understand what is happening, because you never understand what's happening. In fact, most modern CPU architectures, they don't even provide sequential ordering between accesses to memory. They only provide what is called eventual consistency, which basically means that reads and writes are visible by the same thread that did them, but the other thread, it's not really, unless you have a memory fence, it's not guaranteed what it sees at all. And even if you have a memory fence, then you're not guaranteed that the reads and writes before it were in the same order. You're only guaranteed that you see that you impose this particular ordering in this particular place, nothing else. So it always is a distributed system. And that's pretty much what we're dealing with. So, and that's why all the clever tricks. That's why, you know, returning back to this original article where I was called an idiot 100 times. That's why I was called an idiot, because I didn't understand that we're dealing with a distributed system, and that all these clever tricks you can use that you used to work on a single core, they no longer work because of that, because everything is really complicated on the covers. And the next, so are there any questions maybe so far?